Hello, my name is Kambi Samadani, and today I'll be talking about a framework for scalable content development in hands-on virtual and mixed reality science labs. Virtual labs have the potential to enhance learning in STEM fields considerably. The strengths, synergies, and pitfalls of physical and virtual labs are reviewed elsewhere. Briefly, the lack of tactile authenticity in virtual labs remains a stumbling block. For some lab tools, interactions mediated by a mouse, VR controllers, or haptic gloves are sufficient for learning. However, for some of the most important lab tools, tactile authenticity is required for learning. In training applications such as flight, combat, surgical training, and even golf, mixed reality approaches successfully provide the level of tactile authenticity that's required. This project starts with the question, can mixed reality approaches provide tactile authenticity to STEM virtual lab training environments? Actual experiments involve lab tools with limited accuracy and precision, as well as student users with limited skill. This noisy and error-prone data is acquired, analyzed, stored, and ultimately used to draw conclusions about the natural world. Instructors assess the quality of such data as well as the validity of the conclusions drawn from them to provide students with feedback on their performance. Unfortunately, this feedback is also limited and opportunities for iterative mastery are lacking. In contrast, virtual labs offer unlimited opportunities for assessment, feedback, and mastery through repetition. However, the data acquired in such virtual labs is neither individualized nor authentically error-prone or noisy. By using mixed reality approaches to track noisy and error-prone lab tool manipulation, the hands-on virtual reality lab system we present here combines the authentic, noisy, error-prone, and individualized data acquisition and analysis of traditional labs with the unlimited real-time assessment, feedback, and iterative mastery afforded by virtual labs. To achieve these goals, the HOVR Lab system combines STEAM VR tracking, optical tracking, with IR retroreflective beads, bead-based passive optical tracking to detect the poses of handheld physical lab tools manipulated naturally by the user. 3D printed marker mounting adapters are designed and used to rigidly mount the tracking sensors or beads onto each physical lab tool. The positions and orientations of each lab tool-specific handler are then streamed into the Unity real-time engine to trigger events and enable real-time feedback on user performance. Within the virtual lab environment, users receive instructions on what to do at each stage of the experience through a blue display screen. This same display provides feedback to the user on their performance. Standard VR controllers and voice-activated controls allow the user to interact with digital content that does not require complete tactile authenticity. For other lab tools that do require tactile authenticity, mixed reality handlers are employed, but VR controllers can also be used to control for the impact of tactile authenticity on learning in a highly specific manner. Importantly, lab tools and lab instruments are also distinguished based on whether they read or write raw data or process data to the user, or whether they merely serve to manipulate and transfer reagents. Another major need for virtual labs is to enable rapid, cheap, and code-free optimization of virtual lab content by faculty content experts. To accomplish this task, we created a highly structured lab module generation spreadsheet, in which one or more rows of the spreadsheet define particular states of the virtual environment. By defining the milestones that a user must proceed through as they complete their lab activity, Faculty content developers define the logical sequence of the lab experience itself in a code-free manner. Once a lab module generator is created, it is read by the main software to generate a new version of the HOVR Labs experience. Iterative refinement is as easy as updating an Excel spreadsheet. Our preliminary pilot studies with a series of Pipette calibration modules used the following mixed methods research design sequence and included both cognitive and affective measures of learning outcomes. We used the chemical concept inventory to assess incoming and outgoing background knowledge of students, the meaningful learning in the laboratory instrument to gauge cognitive and affective learning, perceptions of the learning environment, and measures for intrinsic motivation, self-efficacy, and user experience in surveys at various points in this research design. We plan to create a total of 12 HOVR Lab modules and test them in a wide range of courses, as shown here, ranging from preparatory chemistry all the way to advanced analytical, organic, and instrumental analysis. Some preliminary results of our tests using a Pipette calibration module in the research design that was shown indicate that students with glasses were uncomfortable using the VR headsets, yet most students enjoyed both the VR and mixed reality interventions and found them to be valuable and innovative. The lab module generator spreadsheet also enabled the rapid customization of lab modules for targeted applications, and students found the feedback on their data analysis and calculations to be quite helpful. I'd like to finish by thanking our funding agencies, NSF and Cal State University System, and also acknowledge the contributions of all the faculty that have worked on this project, the various software developers that have been involved in developing the code base, and also the digital artists who have been involved in the 3D printing and modeling of assets that are used in our experiences. Thank you very much for listening.